Alright, let's set up the integral of f of x comma y comma z equals x plus 2y plus 3z over the set E, where E is the space between z equals 4 plus root 1 minus x squared minus y squared for x squared plus y squared less than or equal to 1. And so the space between that and z is equal to 0 for x squared plus y squared is less than or equal to 1. So let's think about what shape we're getting here. This first part, if you just, for just a moment, don't look at the 4, z equals root 1 minus x squared minus y squared. That ends up being, if you were to square both sides, you'd have a unit sphere centered at the origin. Then what the plus 4 does is it raises it up 4 units. Oh, excuse me, you have just the top half of a unit sphere, right? Because it's just the plus square root. So you have the top half of a unit sphere, which was originally centered at the origin, but shifted up 4 units, is now centered at 0, 0, 4. You also have z equals 0, that's the xy plane. Okay, so this shape altogether, this is my best approximation of actual R2D2, so not just R2D2's head, but really head and body, the entire R2D2 figure. So if we were to set up an integral, first let's just describe the region in set notation, just to hopefully help with what's going on here and organize details. Let's go with x being constants, so negative 1 to 1. And then we could organize. So the thing is, from here we've got this filled in circle of radius 1. So y would have to go from negative root 1 minus x squared to positive root 1 minus x squared. And then what about z? Well, that description of what's going on with z is from here. It's got to be between those two shapes. So between z equals 0 and z equals 4 plus root 1 minus x squared minus y squared. So I did say between and equal, so therefore we have now these inequalities. So z is greater than or equal to 0 and less than or equal to 4 plus root 1 minus x squared minus y squared. So now if we set up an integral, due to the fact that x here is the constants, that should be on the outside. Y only mentions x, should be the middle integral, and then z mentions both x's and y's, so that should be the innermost integral, right? So we should have a thingy that looks like this. So dx, dy, dz, right? So the dx is the outside, dy is in the middle, dz is really, truly completely on the inside there. Z we saw goes from 0 to 4 plus root 1 minus x squared minus y squared. Y goes from negative root 1 minus x squared to positive root 1 minus x squared, and x we saw goes from negative 1 to 1, and the function we're integrating here is x plus 2y plus 3z. Whew. Okay, so this is a little messy, right, as written, but it can be done. Let's just do one step of this. So integral negative 1 to 1, integral negative root 1 minus x squared to root 1 minus x squared. And if we're integrating with respect to z, by the way, let's see. So we'll have like xz. X integrates to x times z. The thing is, when we plug in for z, when we plug in this upper value, we get something. When we plug in the lower value, 0, well, x times 0 isn't going to even do anything. So let's just, sorry to skip some steps, but let's just do this. A couple steps later, we'd have something that looks like this, yeah? So x times the quantity 4 plus root 1 minus x squared minus y squared plus 2y, again, there'd be a z here in the anti-differentiation, which after fundamental theorem of calculus gets replaced. We have a 4 plus root 1 minus x squared minus y squared there, plus the next term 3z is going to, okay, there's finally a z here, so let's see, z squared over 2. So 3 halves z squared, but let's just write a z. That would be an antiderivative. Let's go ahead and replace the z in the z squared with what we're about to replace it with due to fundamental theorem of calculus anyway. Squared minus y squared. Oh yeah, and then there was a square, right? Because it was z squared over 2. Okay, that now dy dx. Ooh. Okay, so we could continue this, but let's say that this is certainly messy, right? You could foil out here and things like that, but actually I'll just comment that this integral at this point, this double integral, it'll be much easier to take this and switch. Easier to switch to polar. Because if you look at this, it's still the region here, x from -1 to 1 and y from negative root 1 minus x squared to positive root 1 minus x squared. That region, it should be just in the xy plane now. It should just be the filled in unit circle. Yeah. So the whole reason why this would be easier is because based on what we see here, so why is it easier? And it's because the region of integration is so circular. It's round. That's the kind of thing that polar coordinates will be good for. And just quick comment, this is the basic idea. Behind what we'll look at in the next section, which are called cylindrical coordinates. Now, let's revisit this question using the same E as we had above. What is triple integral over that region E of the function 1 dv? What would this be? So, the triple integral of 1 over the region E dv. First of all, when we write this out as an iterated integral, so integral -1 to 1, integral negative root 1 minus x squared to positive root 1 minus x squared, integral z from 0 to 4 plus root 1 minus x squared minus y squared of the function 1. Let's get the order right here, dz, dy, dx. We're not going to actually compute the integral, but if you're just integrating 1 the whole time, then what you actually end up getting, this is the volume of R2D2. Like the actual volume, not like volume in quotes. This is going to give you the three-dimensional volume. So let's make sure this makes sense by introducing a formula, theorem, whatever you'd like to call it, and relate it back to some things from the past first. So just like if you looked at the integral from a to b of the function 1 dx, this is the length, right, of the interval a to b, and the double integral over region D of the function 1 dA is the area of the region D. Now the new thing is we have the triple integral over E of, again, if you integrate the function 1, that's the key thing here, then this is dV, then this is the volume of E. Okay? The thing, though, let's just comment, please don't confuse with so these versus those, right? So something here will be different is if you integrate from a to b of f of x dx. So now the function isn't 1, but it's just any general function. Then this is the area under the curve y equals f of x, and the double integral over the region D of the function f of x comma y dA. This is the volume under the surface z is equal to f of x comma y, and then finally the triple integral over e of the function f of x comma y comma z dv. This is the whatever this should be called, volume in quotes, under should probably also be in quotes, the solid, I guess, is that the right word to replace surface? It's this thing in four-dimensional space. If you could draw the graph, I guess, yeah. I'm just gonna write this down. Okay, so in four-dimensional space, there's a graph. Good luck picturing it, right? But we're creating the four-dimensional analog of volume here. So I think the key point, though, going back is, okay, if you have some general function here, you're talking about the area under a curve. Here, I guess you are too, but the area under the curve 1, the function value is 1 the whole time. The area under this curve here, right, from A to B, is the same as just the length of the line segment because the height is 1.